Hello everyone, and welcome back. So this time we're going over absolute dependent motion analysis of two particles. How could this be terrible? It's not actually that bad. It does take some practice though. This is a hard concept, but a simple one once you realize how to do it. It's hard to grasp. Once you master it, it's easy to do. So what we're going to do is relate positions, velocities, and accelerations of particles which are undergoing dependent motion. It means they're attached to each other. So let's jump into some applications. So for example, we have this cable and pulley system, which is shown with this minecart. And we know that the motor M is moving. It's pulling in this cable at some particular speed. Well, if we know how fast the motor M is turning and pulling in the cable, how fast is cart A moving either up or down the incline? So to do this, we're going to have to establish a relationship between the various motions. Each of these ropes is possibly going to be moving at a different speed, maybe not. But at least this guy is going to be moving at a different speed. So if we know this cable speed, I'll go ahead and tell you, the ropes, as long as they're attached, they're going to be moving at the same velocity. But these pulleys will be moving differently. If we know how fast that rope is moving, well, can we determine the speed of the minecart? Can we determine the acceleration of the minecart to make sure that these ropes don't suddenly snap? Well, the slope of the track actually matters in this particular case when it comes to how fast that car is moving up or down. Look at right here, this person with a very horrible idea for getting this chest of drawers up to the third story. Please do not do this. This is just nightmares. Nightmares right here. Okay? So please use a moving company. If you have to do something like this, be safe and have a professional do it. Okay. But rope and pulley arrangements are used to assist in lifting heavy objects. Just hopefully not something that's going to be like an Acme cartoon. Now, we know what the truck velocity is, and we also know the weight of this guy right here. So can we figure out how much force is going to have to be applied to pull this upward, pull it upward and get it going? And also, if we know what the velocity of the truck is, can we figure out what the acceleration of the cabinet is going to be? Lots of things going on here. So there is going to be a relationship between this one's motion and this one's motion based on this rope. And that's what we're going to be learning about in this class period. So let's go through just the basics of dependent motion, and the next time we'll go through an example before I actually have you start doing problems. Now, this is obviously, you might not see examples quite as simple as this, but you obviously have seen, let's see, if you look inside your car's motor, you'll see all the different pulleys being pulled by these same wire. Or, let's see, what's a good one? I mean, if you ever see a crane, one of those giant tower cranes, there is a pulley on the end of that that is allowing it to lift extremely heavy objects. And all that matters based on how it's connected, how it is connected. So right here we have the blocks in this particular figure. They're connected by an inextensible cord. It's one of those magical materials like a frictionless plane or a seat vacuum. So an inextensible cord means that it's completely flexible and perfect in that way, but it does not stretch. It does not stretch at all. So what we realize is if block A moves down, well, block B has to move up. The motion of each block can be related by defining position coordinates, SA and SB, from this mutual origin. They have the same origin, we just have position coordinates that are going along their respective paths. Now, right here you can see the words datum. That's just saying where we say these position coordinates start. The origin is from here. These two datums, which do not have to be mutually perpendicular or parallel, are both originating from that origin. And they're measured positive from the origin. So in the direction of each block. As in going from the datum to the block. Okay, so we know that they have an SA and an SB. We can define that fairly simply. Now, if the cord has a fixed length and it's inextensible, then we can also relate these two together by saying, well, we know what the total length of the cord is, perhaps, and we know that we're made up of this part right here, which doesn't really change. That's just always on top of my pulley, plus SA plus SB. Now, the total length of the cord will not change. It's inextensible. That's a very important one. That one right there, that's constant. It's not going anywhere. And so we learned something. Well, if we want to find the velocity of the blocks, we're going to probably take a time derivative. And what happens to something that is a constant? Well, that's constant, so that length is going to go to 0. And the total length is constant, so that time derivative is going to go to 0, which simplifies things. All we're left with is our two position vectors as functions of time. What it tells me then is, okay, well, my velocity B is going to be equal to negative velocity A. That makes sense for this particular case. It makes a lot of sense because you can see that visually. Your mind can probably process that very simply. It's harder when we have more pulleys and more ropes, but for this one at least, that makes sense. And of course, our negative sign indicates that as one moves down the incline, the other moves up the incline, or vice versa. And of course, we can get our acceleration in a very similar way by, once again, differentiating velocity. No weird components here. Just take our time derivative and it pops out as dv dt is equal to our acceleration. Okay, so next time we'll jump into this example and I'll go through that with you. So thank you for listening. Just remember that we are making a couple assumptions here. This inextensible cord is one of them. We define a datum from our origin, and then that datum is perpendicular to the direction that our item is moving, and it starts from 0 at the origin and goes straight to where those blocks are located. We realized that the total length of the cord, as well as this little section that's attached to the pulley, is always constant, and so when we took a time derivative, it was 0, and from that we could get our velocities and our accelerations related. So I'll see you all next time as we do an example. Goodbye.